You know, the internet kind of feels like magic, right? You type in a website and boom, it just shows up on your screen. But behind all that magic, it's actually working a lot like a giant global mail system. Every single thing you do online is a package. And well, every package needs an address.
So that begs the question, right? With billions, and I mean billions, of phones, laptops, servers, and now even smart fridges all connected, how in the world does that cat video you wanted to watch find its way to your specific screen and not, say, your neighbor's? It's a huge sorting problem, but the solution is actually pretty cool.
And the answer is the IP address, which stands for Internet Protocol Address. This is the absolute foundation of how the internet works. Just like your house has a specific street address so you can get mail, every single device connected to a network gets an IP address. Without this, the internet would just be chaos, a bunch of lost data with no way to get anything delivered.
So, in this explainer, we're going to break down exactly how this digital postal system works. We'll start with the basics, then get into the big upgrade from IPv4 to IPv6. We'll also unpack the difference between public and private addresses, static versus dynamic ones, and finally, how your device even gets its address in the first place.
All right, let's start at square one. The main job, the whole purpose of the Internet Protocol, is to get these little chunks of data, called packets, from point A to point B, even if that's halfway across the world. It's pretty much the Internet's universal delivery service.
So when you stream a movie or send an email, that file isn't sent as one giant piece. Nope, it's chopped up into thousands of these tiny little packets. And each one gets wrapped in a header that's basically the digital version of an envelope. It's clearly labeled with two crucial things: the IP address of where it came from, the source, and the IP address of where it's going, the destination. Then routers all over the globe act like mail sorters, reading those addresses and pushing the packets along the best path until they all arrive at your device.
Now, the original addressing system, which we call IPv4, was designed way back in the early days of the internet. And as the internet just exploded in popularity, it became super clear that the old system was, well, running out of addresses. It was definitely time for a major upgrade.
So this original system, IPv4, uses a 32-bit address. Now that allows for about 4.3 billion unique addresses. Back in the 80s, that seemed like an impossibly huge number. But then came personal computers, then smartphones, and now all our smart gadgets. And we burned through that limit way, way faster than anyone ever thought possible.
And this is where IPv6 swoops in to save the day. Instead of 32-bit, it uses a 128-bit address system, and that gives us 340 undecillion possible addresses. It's a number so big, it's hard to even wrap your head around it. To put it in perspective, that's enough to assign a unique IP address to every single atom on the surface of the Earth and still have tons left over. Yeah, it's safe to say we are not going to run out of these anytime soon.
So let's just put them side by side. The biggest difference, obviously, is the size. 32-bit for IPv4 versus a whopping 128-bit for IPv6. And that's what creates the massive difference in the number of addresses. You can also just spot them visually. IPv4 is that familiar format with 4 blocks of numbers. IPv6, on the other hand, uses a much longer hexadecimal format, with colons separating the blocks.
But you know, the system gets even more clever. To be more efficient and to help conserve those precious IPv4 addresses, we don't actually give every single device its own globally unique address. Instead, we use a really smart two-tiered system, public and private addresses. And the best way to picture this is to think of a big apartment building.
Okay, so your public IP address is like the street address of the entire apartment building. It's the one single address that the whole outside world sees, and it's given to you by your internet service provider. But then, inside your home or office network, each of your devices, your phone, your laptop, your smart TV, gets a private IP, and that's like its own unique apartment number. These private addresses are only used locally, and nobody on the outside internet can even see them. So how does the mail get to the right apartment? Well, your Wi-Fi router acts like the receptionist in the lobby. It uses a process called network address translation, or NAT. When a data packet shows up at your public address, the router looks at its list and says, aha, this one's for the laptop in apartment 101, and it forwards it to the right device using its private IP. This little trick is what lets hundreds of devices in a building share one single public IP, and it was absolutely critical for stretching out the life of the old IPv4 system.
Now, if you've ever poked around in your router settings, you've probably seen numbers like these. The Internet authorities have set aside specific blocks of addresses that are only to be used for these private networks. The one you see most often in home routers is that 192.168 range. Anytime a router sees an address starting with these numbers, it knows it's a private address and not to send it out onto the public internet.
And there's another layer to this whole thing. IP addresses aren't all assigned the same way. Some of them are permanent, while others are just temporary. This is the difference between static and dynamic addresses. A great analogy is having a permanent home versus just staying in a hotel for a few nights.
A static IP is just what it sounds like. It's fixed. It doesn't change. It's like your home address. This is absolutely essential for things like web servers or business systems that need to be found at the exact same address, every single time. It's super reliable, but it usually costs extra. On the other hand, most of our personal devices use dynamic IPs. These are more like temporary hotel room numbers. They get assigned automatically from a pool of available addresses by your ISP. They're cheap and easy to manage, but they can change from time to time, which is why they're not great for hosting a website.
So if most of us are using these temporary, dynamic addresses, how does your phone or your laptop get one when you connect to a new Wi-Fi network? Well, it's not magic. There's an automatic process that works like a friendly welcome desk for any device that wants to join the network.
This whole process is called DHCP, or Dynamic Host Configuration Protocol, and it's basically a simple four-step conversation. When your device connects, it broadcasts a discover message, which is like it's shouting, "Hey everyone, I'm new here and I need an address." Your router, which acts as the DHCP server, hears this and offers an available IP from its pool. Your device says, "I'll take it," by sending a request, and finally, the router sends back an acknowledge message, which confirms the assignment for a certain period of time. It's a quick, automated handshake that happens every single time you connect.
Okay, but what if something goes wrong? What if your device shouts out for an address, but the DHCP server, your router, is maybe turned off or it's not working right, and there's just silence? Does your device just give up?
Nope. It actually has a backup plan called APIPA. If a device can't find a DHCP server to talk to, it just assigns itself a special temporary address from a reserved range. Now here's the crucial part. This address is only for talking to other devices on the same local network. It can't be used to get out to the internet. It's a fallback that lets your laptop still talk to your local printer even if your main internet connection is down.
And that really brings us full circle. At the end of the day, it all comes down to this one core job. The Internet Protocol's whole purpose is to put addresses on devices and then route data packets from a source to a destination. Everything we just talked about, IPv4, IPv6, public and private addresses, it's all just part of this incredibly elegant system designed to get information exactly where it needs to go.
So as we wrap up, I want to leave you with this thought. Thanks to the practically infinite address space we have with IPv6, we're way past just connecting computers and phones. We literally have the ability now to give a unique public address to every light bulb, every car, every sensor, every single object you can imagine. And that raises a really fascinating question for the future. What's the next thing you'll connect?